Hello everyone. Today we're going to look at some concepts in vector spaces. Specifically, we're going to talk about null spaces, column spaces, and linear transformations. The topics we would be covering here are a definition of a null space, how a null space is related to things we have learned earlier like solutions of homogeneous equations, column spaces and its relation with the solution of matrix equation. Once again, we will revisit linear transformations, and we can also talk about the kernel and ranges of these linear transformations. So let's start with a null space of a matrix. Now, when we talk of a null space, it simply is the collection of all solutions of the homogeneous equation Ax equal to 0. Remember, homogeneous equation is an equation of the form Ax equals 0. So what now we are doing is we are collecting all the solutions which satisfy this homogeneous equation. When we gather them together and we call that set the null space of A. And we denote it by null A. And here we're looking at a matrix of size m by n. So once again, the null space of a matrix of a size m by n is the set of all solutions of the homogeneous equation Ax equal to 0. And here's in the more concise or set notation form. Now, I would like to show you certain things. So how, when we look at it from a graphical point of view, suppose this is my Rn. Okay. Now, what is null space? Null space means looking at elements, those elements in Rn. Suppose we are looking at these elements. I have a certain smell. So I have all these elements in Rn. And when the matrix A acts on these elements of Rn, all of them, they are mapped to an element of 0. Now, if you can recall back to your things of linear transformations and how they're related to a matrix equation, that's what we are having. So remember, if you have A, a matrix from m by n, when on this acts on this vector x, which is an n by 1, in a homogeneous, they're all mapped to the 0 vector. And if we translate it into the linear transformation, the matrix transformation world, it is transformation from Rn to Rm. So what is my null space doing? Null space says all the elements in Rn, when acted upon by the matrix A, is mapped onto the 0 vector of Rm. Okay. So remember, we said we're going to revisit linear transformation. So here we are visiting it. And what we are literally looking at is a matrix transformation, because this matrix transformation happens because of this matrix multiplication. Now, let's look at a very important theorem here. And that is the null space is a subspace of Rn. Keep in mind, every time when we're talking of a matrix A, we are looking at a very general matrix A of size m rows and n columns. So null space, which we just said, is a set of all solutions of the homogeneous equation Ax equal to 0. Remember that. Okay, this x is an element of Rn. So now what this theorem says that the null space of A is a subspace of Rn. We are going to prove that it is a subspace. Now if you go back to your previous section where we just talked about vector spaces and subspaces, there we said if you want to prove something is a subspace of a vector space, then you have to prove that set is a subset of that vector space. It includes a 0 element. It satisfies the closure additive property and satisfies the closure of the scalar multiplication. So we're going to prove those 4 things. The first thing is Rn, if you remember, is a vector space. Remember, Rn is the vector space. Okay, this is a vector space. Now null space is a subspace. Sub, as the name suggests, first of all, you prove that it is a subset of Rn. Now, it is a subset of Rn because what is the collection? What is null space of A says? By the virtue of the definition of the null space, it's all those elements X where X is an element of Rn and Ax is equal to 0. So clearly, null space has all the elements which are in elements of Rn. So by the virtue of its definition, null space is a subset of Rn. Or we can also look at it in the form of that these x's, they are nothing, but and you can think of that as that your A has n columns. There's another way of looking at it. So when I say it's a subset of Rn, by the virtue of the definition, it actually is. And also if you want to say because A has n columns, you can also think of that too. Okay, the second thing we prove is in a subspace that the 0 vector should belong to the null space of A. So if it's a 0 is a vector in null space, that means according to the definition of the null space of A, when A acts on 0, okay, when A acts on 0, we should get 0. Now any matrix when multiplied by a 0 vector will give us a 0 vector. Now remember this 0, guys, this 0, which is the one here. So let me just use colors to show you that. So this 0, so when I say A times 0, so this 0, guys, is this. So this 0 is here. When A is multiplied to the 0 vector, this 0 vector is in Rn. Keep in mind, the 0 is in Rn. And when A multiplies to 0, we get another vector. Okay? And that vector, guys, is a 0 vector, but this 0 vector is in Rm. Okay? So certain things to keep in mind. The background, keep in mind which dimensional spaces we are working in. So when I say 0 is an element of null space of A, yes, because any vector when multiplied to a 0 vector will be a 0 vector. But we also keep in mind is which 0 vector is happening when. So the red one which you see when A acts on it, that is a vector which is in Rn. And when you multiply A, now remember here, so let me show you this one. So if A is m by n, and this 0 is n by 1, you remember this is going to be a 0 vector, but it will be a vector of m by 1. Okay, so we have proved 2 important things relevant to being a subspace. Now we're going to prove 2 more, and that is that if we have 2 elements in the null space of A, then the sum of those 2 vectors is again in the null space of A. So what this basically we are proving, guys, over here is that we are going to prove that the closure property of vector addition. So here it says U and V are 2 vectors in null space of A. So what does this mean? If U and V are 2 vectors, what means if U is in null space of A, what does that mean? A times U is 0. If V is an element of null space of A, that means A times V is 0. Remember, that's the way the definition is of a null space. Now, what the thing we have to prove is that if 2 vectors are in null space of A, you add those 2 vectors, again it should be in null space of A. Okay, so we have to prove that U plus V is in null space of A. In other words, you have to prove the property that when A acts, because remember, every time you're thinking of null space of A, keep in mind, what is the definition? X, when X is in Rn, and Ax equals 0. That is the background we need to keep in mind. So when I say A null space X, that means U plus V, that means this condition Ax equal to 0 has to be satisfied. That means when A acts on U plus V, has to be 0. Now remember, we're going to apply the matrix properties. You're going to distribute A to U, the two vectors AU plus AV, which is 0 from here and 0 from here, it's 0. So therefore, the vector addition is closed in the null space of A. Now we have to prove the closure of the scalar multiplication. Now if alpha is any scalar, we got to prove alpha times U is in the null space of A. Now clearly when U is in the null space, you already know that. So if it is in the null space, what do we say? Take the matrix A, multiply it to the vector alpha U. Once again, the matrix property says as alpha is a scalar, you can take that out. A times U, because U is a vector in null space of A, it is alpha times 0, it is 0. Therefore, alpha U is in null space of A. And what do we have just proved? We have proved all the 4 conditions required for it to be a null space. Thus, we see that null space of A is a subspace of Rn. Now let's do some examples. First thing is, we want to prove, is the vector 5, minus 3 and 2 in the null space of A, where A is this matrix. Before we even start applying the condition, remember, we have to make sure that the element in null space actually is in the Rn. So in other words, whenever you have to prove that, okay, let me just talk about this, let me repeat again here. So when we talk of null space of A, the first thing always to keep in mind is, it is all those element x, where x is an element of Rn. A times x is 0, and A is an m by n matrix. This is very important definition to keep in mind. So now, when I want to prove that is this vector in the null space, I have to make sure first of all it is an Rn. Now my n over here is 3. Let's look at this one. This matrix A is what? This is a 3 rows by 3 columns. So x, first of all, the element x here, this one, it's important x should be in R3. I'm using the green to say this n basically is the number of rows, very important, sorry, number of columns. The green matches the green, okay? The number of columns is where the vector should be going to. So x is an element of R3. So yes, it is true because our vector we are looking at is an R3 vector. So we are good to go. Now what do? We take the matrix A and we multiply it to x. So this matrix is what? 5, 21, 19, 13, 23, 2, 8, 14, 1. Okay, let's have this vector 5 minus 3 and 2. Now you can easily do the math. I will just simply write down the answer. It is 0, 0, 0. So clearly, when A multiplied with this vector, the property is proved. And hence, we say that the vector 5 minus 3 and 2 belongs to the null space of A. So this is right. Okay, let's look at another example. Now in this example, I'm asking, is the vector 5 minus 3 and 1 in the null space of B, where B is a 3 by 3 matrix. Okay, B is a 3 by 3. So just to make sure that I'm going to emphasize with the row and the columns. So I'm working with, if it is an element of null space of B, now clearly, suppose this is the vector x, or say y, doesn't matter. So y definitely belongs to R3, that is the number of columns. Yes, it is true. So if I want to prove that this is an element, so what do I have to do? B times y should be equal to 0. Remember, every time null space of B is what? Null space of B is all those y's where y is in R3 such that B times y is 0. Now, if B times y is 0, then you're good to go, and we say, yes, this y is an element of null space of B. Now, just go ahead and do the simple math. We write down B, which is 5, 21, 19, 13, 23, 2, minus 8, minus 14, 1, and we have 5, minus 3, and 1. Now notice the first two rows of both these matrices is same, and is basically the previous one. So this matrix and this is kind of same. So I already know the answers from the previous slide. This is the one which I have to look. So minus 8 times 5 minus 40 plus 42 plus 1. So it is 3. What does that say? When I multiply b with y, I do not get a 0. Thus, y does not belong to, that's the symbol, okay? Does not belong to R3. Oh, sorry, null space of 3, what I'm saying. Y is an element of R3, sorry, it does not belong to null space of B. Sorry. Okay, now let's look at another example. Here we have a vector which is a 3 by 1, 2, 3, 1 here, and we have a matrix C. So you want to know, is this vector 2, 3, 1 in the null space of C, where the vector, matrix C is a 3 by 4 matrix. Okay, that's the size of the matrix. So remember once again, if this vector in the null space of C, what does that mean? Null space of C means all those k's such where k is an element of R4. Very important. Okay, all those k's were element of R4. This 4 and this 4 guys should match. And A times, so not A but C here, C times K should be equal to 0. So two things to take in mind. This vector K has to be first in R4. Okay, let's look at the vector we are given. We are given the vector 2, 3, 1. Where is this vector, guys? This is a vector in R3. So it can't even go into null space of C because this is not at all a vector in R4. So what do we see? Before we can even prove that it satisfies the condition, it is not even an element. So clearly, the vector 2, 3, 1 is not an element of R4. Thus, this vector 2, 3, 1 does not belong to, is not an element. So this one, guys, is like this. Is not an element of null space of C. Okay? Okay. So let's look at some more features of null space. Now, what did we say? What's a null space? Let's look at this one. Suppose A is an M by N matrix. And what did we say? Null space of A. All those x's, they are in Rn such that Ax is 0. Now, in a very general form, it is a subspace, okay? Clearly, we just proved that it is a subspace. Subspace means every subspace is a vector space. Remember that, okay? It has infinite elements. That's what I'm talking about here. What did we just prove? That the null space of A is a subspace of Rn. And we also know that every subspace is a vector space. Now remember all those 10 axioms. So if you take any two vectors, all possible linear combinations of those vectors. If you take a set of vectors, so all possible linear combinations of the set of vectors will be an element of the null space of A. So what does that mean? If you have a vector space or a subspace, that set is going to have infinite elements. Now that's going to be a big issue if you want to prove certain things. So the next question is, as this set has infinite elements, can we represent this set by a fewer number of elements? And then even when we do so, when you look at those fewer elements, automatically when we take linear combination of those fewer elements, we get the whole space. That means we get all those possible infinite elements. So those fewer elements control everything. And the question is, can we represent it? Can we represent this null space by a finite number of elements? And yes, it is possible. So what I'm basically saying is this, in the language of what we have learned. I'm saying, can I write my null space as a linear combination? Remember the spanning set, the spanning set? So it's a linear combination of fewer, or I would say fewer finite. I won't say the word fewer, but a finite is the right word. Of finite elements, linear combination of finite number of elements of Rn, which, if you remember, is a definition of the spanning set, or it is the span of, say, V1 up to Vp. Where are these VIs belonging from? These VIs is an element of Rn. That's what I'm saying. So we said, yes, if we have an infinite elements in a set, that infinite element set can be represented by a finite number of elements. And the way we do it is, that means we look at the spanning set. And the spanning set of those few vectors, which are an element of the vector space Rn. Okay. So let's go and see how we can do that. So I'm going to explain it with the help of an example. How do we write a spanning set of a null space of A? Okay. We have a matrix A, and we would like to find the spanning set of the null space of A. This A, first of all, let's look at the size. Now remember, every time you're given a problem, the first thing I've always said to you is write down the size of the matrix. It controls a lot, it has a lot of information. Okay, so first of all, we see 3 rows and 4 columns. So this A is a matrix of size 3 by 4. Okay, that's taken care of. And also, if you recollect that these 4 columns are kind of giving us the 4 variables also. Okay, so in order to find the spanning set, what are we basically doing? We want to find the general solution of Ax equal to 0 in terms of the free variables. What basically we are saying is, things we go back to a homogeneous equation. We say, can we write down the solution set of the homogeneous equation in the vector parametric description form? That's what the simple line says. In this one, it says find the general solution. What basically this is saying, write, that's what basically the bigger picture is. Write, we have to find the general solution. In other words, write the vector parametric description. So it's the vector parametric description of the solution set of the homogeneous equation, which is Ax equal to 0. Okay, so what are we going to do? Now, either we could have applied straightforward over here, or we can make our life simpler. We can row reduce this matrix into the echelon form and then write down basic variables. Because remember, when we row reduce it, the solutions of the row reduced matrix is the same as the solution of this matrix A, because those are equivalent matrices. So what we're going to do is first row reduce this argument matrix into a reduced echelon form. So I've done the work for you guys over here. So we start from A, we go from here, and then we go from here to here, and the final step is here. So at this point, I know you guys already know how to do that, so I have written down what are these row operations over here. Okay, so I'm going to focus on this final echelon form of the matrix A. Now this is the one we want to write down the solution set. Remember, what does that mean? It means now to find the solution set, what are we going to do? This Ax would be now 1, 0, 2, minus 1, 0, 1, minus 1, 3, 4 zeros. And remember this vector x, because this vector x has to be an element of R4. So we're going to have x1, x2, x3, x4. Remember matrix multiplication, 3 by 4 and 4 by 1. And this is equal to 0, 0, 0, or 3 by 1, 0 vector. Okay, so first we row reduce it. Once we have done the row reduction of this matrix, we need to find this variables. Now, how are these variables interrelated? If you remember that the basic variables will be written in terms of the free variables. That's an important part if you remember your vector description set of the parametric form. So here, what are my basic variables? Just a quick recap, guys. This is my basic variable. This is my basic variable. So what do I have? The two are the basic variables. And by default, we assume that the first column represents the variable x1, second is x2, third is x3, and fourth is x4. And the last two are my free variables. This is chapter 1, guys, the earlier sections. Okay, now we're going to write down the basic variable in terms of the free variables. So x1 plus 2x3 minus x4, when you put this is the general solution. Now remember, this is called the parametric description. What I'm looking is parametric vector description. Okay, so what I wanted to write down is this vector x. Remember what we're looking at, Ax equal to 0. I want this vector x, because what is my null space consisting of? It is all those x's where x is in R4 and Ax equals 0. So I am basically looking at this x. So in other words, what is this x? This x is x1, x2, x3, x4. So I want to write this x1, x2, x3, x4. So what are we going to do? We have this vector description, the parametric description of the solution set. And we already know x1 and x2 are the free basic variables, x3 and x4 are the free variables. And if you remember, we have done a lot of practice of writing this vector parametric description set. And we write x1, x2, x3, x4. x1 is what is in terms of x3 and 4, and x2 also in terms of x3 and x4. And then these two remain as it is. Now what are we going to do? We're going to do our normal vector addition and scalar multiplication. First of all, we will gather the x3's together. And if you remember, this one is what? It is minus 2x3, x3, x3, 0. Plus it's x4 minus 3x4, 0, x4. And from here, what we're doing is now we're taking the x3 out, we go here, we take the x4 out from the last vector, we get here. Now, what is the null space? Now notice, what is this x1, x2, x3, x4? It is all possible linear combinations of the vector -2, 1, 1, 0 and 1, -3, 0, 1. All possible linear combinations. So basically, the null space of A is actually being controlled by these two vectors. So what we notice is that the null space of A, which actually is a subspace or a vector space, has infinite elements, is basically in the hands of these two vectors only. You look at all possible linear combinations, you get the original null space of A. Okay, let's look at some observations. If I have a matrix A of size m by n, a null space of A is a subspace of R to the power, which is the number of columns of the original matrix A. It is implicitly defined. In other words, in order to find the null space, I have to do a lot of work. Okay, remember once again, null space of A is all those x's where x is in Rn and Ax equals 0. So it's not that clear-cut that how can I write null space in terms of A. You have to do a lot of work to come to the spanning set of A. That's why it is implicitly defined. And if I have an element of null space of A, a vector V, it will always satisfy that A times that X element of null space of A will always go to the 0 vector. Now, how many vectors are going to be in the spanning set? It is always equal to the number of free variables. Very important. When you're looking at the homogeneous equation, you apply the row reduction algorithm and you write it in the echelon form. What you'd see is the number of free variables automatically tell us how many variables or how many elements are going to be there in the spanning set. And then further, a spanning set of null space is automatically linearly independent if the null space has no non-zero vectors. Finally, if my null space is only consisting of the 0 vector, or it is a 0 subspace, and if that is the case, then the equation Ax equal to 0 has only the trivial solution. Remember, this means it is the 0 subspace. If null space, we know, is always a subspace. If it is a 0 subspace means it only has the 0 vector. If you remember, it is a trivial subspace. So if my null space only is a trivial subspace, only containing one element, that is a 0 subspace 1, then in that scenario, it is only going to happen if the equation, homogeneous equation Ax equal to 0 has only the trivial solutions. Now, I have given you some practice questions at the very end of this, lecture notes. And let me just show you where they are. So I would like you to start practicing these problems, say around 1 to, I would say 1 to 5 would help you with the null space problems. And then we'll talk about, so 1 to 5, guys, definitely are problems related to the null space of A. So please go ahead and start practicing them. Thank you.